So it's a great pleasure being here in this beautiful city and reconnecting with old friends and chatting with new colleagues. So I'm going to speak about continuous Bose-Einstein condensation and superradiant clocks. And this is research from the field of ultra-cold quantum sensing. So the best clocks, optical clocks in the world are atom interferometers work using atoms, and they are just standard pieces made by nature, and therefore these measurement devices are much better than if you would use as your reference, say, a human-made pendulum which changes its length all the time if the temperature changes, for example. And the best optical atomic clocks, they have a precision of 10 to the minus 18. That's 1 second off over the lifetime of the universe, or just 1 centimeter height difference in the gravitational field of Earth if you look at gravitational time dilation. And atom interferometers can sense accelerations and really good for navigation, inertial sensing, or underground exploration. Now, ultra-cold atoms are great for quantum sensing because you get rid of the Doppler effect and you can keep them a long time in your vacuum chamber, and so you can enhance your measurement time. And these devices are really great for many things, for example, in fundamental research, test of relativity, QED tests beyond standard model physics. You can also use them to explore many-body physics. In the future, they might be used to detect infrasound gravitational waves, and in society they are of course useful for network synchronization or navigation. And we want to contribute to this field with 2 research lines. In the first, we are trying to build a continuous atom laser. And so far, we achieved a Bose-Einstein condensate that lives for as long as we want. And on the way to creating this, we created a technique that can provide a continuous ultra-cold beam of strontium atoms in the dark. And it turns out that this continuous intense thermal beam of atoms is already very good for quantum sensing. And we are on our way to build various continuous clocks based on this source of atoms. Okay, let's start with our continuous atom laser work. What's a laser beam? A laser beam is a propagating wave that describes many particles, an electromagnetic wave that describes photons, or a quantum mechanical matter wave that describes atoms. And laser beams are just much nicer for precision measurement than thermal sources of particles because they have better brightness, divergence, spatial mode structure, and coherence. And how do you go about creating a laser beam? Now, in optics, you just put an inverted gain medium into a cavity, and eventually spontaneous emission will populate a mode of your cavity, and stimulated emission will amplify this mode. And then if you make one of the mirrors a little bit transparent, you obtain a laser beam. Of course, after a short time, the inversion of your gain medium has decayed and the lasing stops unless you pump your gain medium. Now, this principle translates 1-to-1 to an atom laser beam generation scheme. Yeah? So we prepare an ultra-cold sample of atoms in a trap, and we make this gas really dense and cold such that its phase-space density exceeds the threshold for Bose-Einstein condensation. And then elastic collisions will drive atoms into the ground state, and this mode will then be more and more populated by Bose-enhanced elastic collisions. And if you somehow punch a hole into your trap, you can outcouple atoms from your BEC and obtain an atom laser beam. Of course, this beam also stops because after some while you have used up all your atoms, and so you need to pump the system by putting new atoms into the thermal gas surrounding the BEC, and you need to guarantee that these newly arriving atoms, that you take away their kinetic energy, for example by laser cooling, so that you always have a really high phase-space density in the thermal gas surrounding the Bose-Einstein condensate. Okay, we are not quite there yet, but we already achieved a Bose-Einstein condensate that lives for as long as we want. So in a sense, we have created the equivalent of a continuous wave optical laser with perfectly reflective cavity mirrors. We are currently working on outcoupling schemes. Now, people have created atom laser beams since like over 20 years. And they do this in a pulsed manner. You laser cool a gas, you perform evaporative cooling, you get a BSC, and you outcouple, and you get beautiful atom laser beams. But they stop if you want a reasonable flux after 100 milliseconds or so. And then you need to produce a new BSC, which can take seconds. So these devices have very poor duty cycle, and that's a reason why they are not useful for quantum sensing. Now, since over 25 years, people wanted to produce a continuous atom laser beam. And one way of doing this is obviously clear. You have to execute all these cooling stages at the same time, but distributed over space. And there has been a lot of progress on elements of this scheme over the decades, but it wasn't pushed through all the way to continuous Bose-Einstein condensation. And one reason for that is that all these precursor experiments, they used alkali atoms or chromium, and they can't be laser cooled very well. Another problem is that the Bose-Einstein condensate is not really compatible with laser cooling light. If you have an atom in a BSC, it essentially stands still, and as soon as it absorbs a stray light laser cooling photon, it obtains a momentum kick of that photon. It's a thermal atom, and it's lost. Now we are working with strontium, and that gives us new possibilities to tackle these challenges. We do have a broad line width laser cooling transition, 30 megahertz wide. It's in the blue spectral region. And that's very nice to slow the hot atoms coming out of an oven, the fast atoms. You need a strong laser cooling transition, but you can't cool very well. However, we also have a 7 kilohertz line width cooling transition in the red, with which we can cool much better down to the microkelvin regime. Furthermore, we have a trick with which we can render our atoms transparent against these red laser cooling photons. And when we were still working in Innsbruck, we performed an experiment in which we showed that we can create a Bose-Einstein condensate in thermal contact with a laser-cooled cloud of atoms. And this scheme forms the core also of our new continuous atom laser machine, so I will show it to you now. So the Innsbruck scheme worked in a pulsed way. We first pre-cool a sample of strontium atoms using this strong blue transition. And then we switch over to the red transition and cool from a millikelvin to a microkelvin. Next, we load these atoms into an elongated optical dipole trap. We call this a reservoir. Here you see the distribution of our atoms. And because you levitate the atoms now against gravity with a dipole trap, you can reduce the intensity of these laser cooling beams. They don't need to support against gravity anymore, and you can reach already a decent phase space density of 0.1. And remember, after Einstein, we need to be above 2.6 for Bose-Einstein condensation. Now we enhance the phase space density with a standard trick, the dimple trick. We make the potential a little bit deeper in the middle, and you see how the density of atoms increases. They flow in there, and they thermalize by elastic collision with the laser-cooled cloud around it. They become denser. But we can't yet get a BSC because of all kinds of bad effects from our photons, like photo association, molecule formation, multiple scattering, diluting our gas. And therefore, we now apply yet another laser beam onto the center of our cloud. And this laser beam AC Stark shifts the optically excited state of the narrow laser cooling transition far out of resonance. And then the atoms, as you can see here, become transparent. Now, by putting in everything together, we obtain a BSC in the center of the dimple. We can't see this in situ. Our resolution is just not good enough, so we just switch all the laser beams off, let the atoms drop, make an time-of-flight expansion image, and here you can see the thermal cloud of atoms, which has a Gaussian isotropic shape, and the BSC, which has an elliptical shape. That's just because of the release of interaction energy, mean field interaction in the BEC, which is predominantly in one direction. Okay, now we have already the central part of our continuous atom laser machine. What's missing is the outcoupling and replenishing the BEC with new atoms. As it is, it would just die after a second or so because of three-body recombination. Now, replenishing the atoms, that needs us to use this broad line width transition. Yeah, it's the only one that can slow the fast atoms from the oven. However, we can't protect our atoms with the transparency beam trick from these photons. So we built a new machine where we separated the blue laser cooling stages spatially from the red laser cooling stages. And here you see how this machine looks like in the lab. Yeah. And over here you have an oven, a Seemann slower, a blue 2D mod sending atoms downwards. In the lower chamber the atoms are, there's a vertical Seemann slower, and then the atoms are trapped in a red magneto-optical trap. And this region is still a little bit too bright. We can't make a BEC there, so we push the atoms into a guide and send them to a really dark region of our chamber. And that's where we have this whole scheme with reservoir, trap, dimple, and transparency beam. Let's zoom in on this. So in this artistic rendering, you see the atoms falling down, the red mod. Yeah, in reality, the atoms are red, of course, but blue looked much cooler, so we told the artist to do it like this. So here's our guide. We slow these atoms here with a third teeny tiny Seemann slower and shuffle them into the reservoir. So in reality, it looks like this. The guide, here's the slowing and turnaround region, and here this part is just like in the Innsbruck experiment: reservoir, dimple, and transparency beam. And again, we can't see much in situ, so we switch everything off and make time of flight images. Here you see this haze comes from the atoms in the guide, turnaround region, and here reservoir and dimple. Now in this image there's nothing elliptical, so no BEC. Let's make a few experiments. We suddenly switch the machine on, load atoms for 1.1 seconds, and then switch everything off and take this image. And you see the reservoir fills a bit. Now we do a second experiment where we load a little bit longer and longer, and you see that the reservoir and dimple, they are filling up. And then if you load longer, you obtain this tiny elliptical feature on top. And otherwise, at some point, nothing changes anymore. And this is because the system has entered a steady state. In the dimple, the gas density is really high, 10 to the 15 atoms per centimeter cubed, and we have a lot of three-body recombination and losses. 120,000 atoms per second are just burned away. But we compensate for this by continuously putting new atoms into the laser-cooled reservoir. And so yes, we have the system is in steady state for as long as we want, and now we need to just show that this elliptical feature is a BEC. And how do we do this? We fit an appropriate model to it. So here I take two images with short and long loading time, and I just fit a thermal model. I assume we don't have a BEC. And a thermal model, that means just Gaussian distributions for the various regions that we have. Yeah? And you can see that fits the image with short loading time really well, but if you apply the same model for the image with long loading time, it just doesn't work anymore. And then if I add what I expect for the BEC, you see my new fit function describes this also perfectly well. And we checked, of course, that the BEC is created at the right moment, that it has the correct size and shape, and so forth. Okay, so we reached continuous Bose-Einstein condensation, and we have this driven dissipative system. Yeah, so perhaps some of the things Andre talked about could be explored here. And currently we are looking at various schemes to outcouple an atom laser beam from the system. Now, on our way to create this continuous wave Bose-Einstein condensate, we created this continuous microkelvin cold strontium beam in the dark that resupplies atoms to the reservoir. And this beam already is very useful for quantum sensing, and we are using it now to build various continuously operating clocks. Now, normal clocks don't operate continuously. Yeah, you prepare a sample of, say, strontium atoms with blue and red laser cooling, put them into a so-called magic wavelength optical lattice to suppress the Doppler effect completely, and then you perform spectroscopy. And typically, this spectroscopy destroys the atomic ensemble, and you need to create a new one for the next spectroscopy pulse. In this way, you lock your laser onto the atomic transition, and the output of the laser, that's your clock ticking, like at 460 terahertz. Okay, now these lasers, they are of course a little bit nasty. They don't stay put on us at a certain frequency all on their own. They fluctuate around in frequency and drift around. And if we interrogate this laser only once in a while, interrupted by dead time, that leads to a problem. So here I plot like the relative frequency between our laser and the atomic transition. Assume the atomic transition is just stable, so you see the laser's fluctuations in frequency. And now I prepare atoms and I measure. And I need to prepare new atoms and measure and so forth. If I want a high precision, I obviously average my measurement results, so all these blue lines, and I get this result. But if you would average the whole signal, you would have obtained this true average, which is different. So you have an error. There's an error from the so-called Dick effect, downsampling of high frequency noise of your laser into the measurement result. So this is one problem of pulsed measurement, but there's perhaps an even more severe one. Assume you have a large time t available for your measurement. Now typically you cannot measure very long because the phase coherence of your laser just isn't good enough. You need to interrupt your measurements once in a while, otherwise you lose track of the phase. So you need to make lots of little measurements separated by these preparation times. Then each measurement has at the best a Fourier limited precision of 1/tau, and then the precision after averaging, it scales with the square root of the number of measurements. So with the square root of the total measurement time that you have available. And that's not particularly good. Assume you had been able to measure coherently for the whole time that you have available. Then the Fourier limit is of course 1/t, and the precision that you can reach scales with 1 over the time that you have available. That's completely different than 1 over square root of time. Now the best clocks, they do reach 10 to the minus 18 precision after 10,000 seconds of averaging, 3 hours of continuous pulse data taking. And if you could change the scaling behavior, you would be able to achieve the same thing, not in 10,000 seconds, but in 100 seconds. So from 3 hours, you go to 2 minutes. So that increases your measurement bandwidth if you're interested in dynamic phenomena, such as gravitational waves or so. And it also makes it much easier to benchmark your clock, to debug it, to make it better. Yeah? Nowadays, if you want to characterize a clock, it takes you half a year. And this is because it takes 3 hours for one single data point. Yeah. So it would be really nice if you could construct continuously operating clocks. And for that to work, you also need a really high signal-to-noise ratio. So you need an intense source or continuous source of ultra-cold atoms. And this thermal continuous atomic beam that we have right now, this is a very nice source for this kind of continuous clock. So let's make use of it. And we built different clocks based on it. One is a passive clock. So usual clocks are passive. You send a laser beam onto your atoms for spectroscopy. The atoms react and are excited or not. In the new clocks that we have built, we use these clocks are active clocks. So you you prepare a continuous beam of ultra-cold strontium atoms, which you excite to the upper clock state. You send them through a cavity, and there you entice them to emit a photon into the cavity mode. And out comes a laser beam directly on the millihertz line width clock transition of strontium. Now, this is a laser, but it's not at all a normal laser. In a normal laser, you use stimulated emission to get your photons, right? So you need a good cavity to get a strong electromagnetic field in your cavity. That means that the cavity has a high finesse and typically a mode that's much narrower than the gain bandwidths that you have in your cavity. So the frequency of the outgoing light is really determined by the length of this cavity. And if, like Brownian motion, temperature, sound, acoustics change the length of your cavity, the phase of the outgoing light will change, and that's very bad for a clock. Now, in a superradiant clock, you inverse this. You, by purpose, build a very bad cavity, such that the cavity line width is much broader than the gain width, than the line width of your atoms. Of course, in that way, you never build up much power in your cavity, and you cannot rely on stimulated emission to give you the photons. But what happens is that the little bit of electric field in the cavity, it couples these dipoles very strongly with each other. And so they behave collectively. It is as if you would have a much, much stronger emitter suddenly in your cavity, which emits light much faster than you could ever expect by spontaneous emission or so from a millihertz line width transition. It's a little bit like a phased array antenna, if you're familiar with this scheme. Good. Now, we are building various versions of this. What's important is that if you have length fluctuations, your cavity mode wiggles around a little bit in frequency, but as you can see, the frequency is dominated by the atom, so the phase is stable. Now, we ultimately want to build a machine that produces a continuous laser beam on the millihertz line width clock transition of strontium, but that's really hard. So we started with a machine that has the ambition to create such superradiant lasing just on the kilohertz line width transition. And you actually can do this already with just a hot atomic beam out of an oven. Just need a little bit of velocity selection and optical pumping methods. And you send your inverted sample through the cavity. And currently, if you inject the cavity with a teeny tiny bit of light, it's working already as an amplifier. So we get 15% more light out of the system than we put in. And we are upgrading the system now with a stronger source and better, a little bit higher finesse cavity, and then it should lace. And this is our new machine with which we try to achieve lasing on the millihertz line width transition. And you see it's the same structure as a continuous atom laser machine. Yeah, oven, blue mode, red mode, science chamber. We load the atoms into a bow tie ring cavity, and hopefully superradiant lasing on the millihertz transition will come out of this one day. Within Quantum Delta NL, a new quantum initiative of the Netherlands, we also built yet another type of continuous clock, which is much less risky than these superradiant clocks. We just use our continuous source and shuffle atoms in an alternating way into two interrogations chambers. And so we have kind of two clocks in one. And then we can also continuously measure. That has been done, but with huge independent clocks so far, and now we integrate everything into one chamber. And actually we have 4 interrogation zones. Good, so that's what I wanted to tell you about. We have a continuously existing Bose-Einstein condensate, and we are working towards continuously operating clocks. These are some of the experiments in the field of quantum sensing in our group. We also have quantum simulation experiments on rubidium-strontium molecules and single strontium atoms in tweezers coupled by Rydberg interactions. And all of this is, of course, only possible if you have a great team of people, so I'm honored to be working with all of these people. So, and I thank you for your attention.
Thank you very much. We have time for a question or two.
Nice talk. I think I missed the main point of going from 1 over square root of t to 1 over t. Is there any assumption that you have to make that the coherence time is maintained through the very long time?
Absolutely. So Exactly. So for example, in the last clock vector I showed you with this alternating ensemble, you have Ramsey interferometry where you share a pi over 2 pulse. So you start interrogation of the first, and the same pulse that you use to stop the first Ramsey interrogation, you use to start the second one. And like this, you get a signal in short time snippets about the relative phase between your laser and the atomic ensembles. And then you can feed back on your laser all the time, and then essentially you have a phase coherent measurement for this whole long period.
But if there's any dephasing of the atomic effect, fluctuation, magnetic fields, this will not work? You assume here that the atomic level is precise?
Yeah, of course. So if your magnetic field fluctuates or something like this, your clock is just bad, just like, yeah.
Someone else?
Thank you. That was a great talk. So I wanted to ask you about the steady state BEC that you have there. So do you have any, if you wanted to probe just the BEC part, would you be able to disturb the steady state and get everything out and just look at the BEC itself? Only work with that? Or is that a little naive?
We can filter a little bit. So using this transparency beam trick, we can at least shoot away all the atoms that they're outside of the dimple. And then we are not completely left with the BEC. There's still a bit of thermal gas around. And also, perhaps we can discuss in the coffee break a little bit more.
So let's thank the presenter once again.